Young's double slit experiment. Fig 9.3 shows the experimental arrangement similar to that devised Young in 1801 for studying interference effect of light. A screen having two narrow slits effect of light illuminated by the beam of monochromatic light. The portion of the wavefront incident on the slit behaves as a source of secondary wavelets. Huygens principle: the secondary wavelets leaving the slits are coherent. Superposition of these wavelets results in the series of light and dark band fringes which are observed on the second screen placed at some distance parallel to the first screen. Let us now consider the formation of bright and dark bands. As pointed out earlier, the two slits behaves as coherent source of secondary wavelets. The wavelets arrives at the screen in which a way that some points crest fall on crest and throw resulting in the constructive interference and bright fringes are formed. There are some points on the screen where crest meet through giving rises to destructive interference and dark fringes are thus formed. Young's double split experiment of interference of light ये डायग्राम दिया गया है ये डायग्राम आप देख सकते हैं Next, order to derive equation for maxima and minima and arbitrary point P is taken on the screen on one side of the central point O. AP and BP are the path of the rays reaching P, the line AD and the paths of the rays reaching P. The line AD is derived the path of the rays reaching the light AD is drawn such that AP equal to DP. The separation between the centers of the two slits is AB equal to D. The distance of the center of the two slits is AB equal to D. The angle between CP and CO is theta. It can be proved that the angles AD equal to theta by assuming that AD is linearly normal to BP. The path difference between the wavelets leaving the slits and arriving at P is BD. It is the number of the wavelength contained within the BD that determines whether bright or dark fringes is appeared at P. If the point P is have bright fringes, the path difference BD must be the integral multiples of wavelength. Thus BD equal to m lambda where m equal to 0, 1, 2 since BD equal to d sin theta. Therefore d sin theta equal to m lambda. It is observed that each light fringe on one side of O has symmetrically located bright fringes on the other side of O. The central bright fringe is obtained when m equal to 0. If a dark fringe appears at the point P, the path difference BD must contain half integrals number of wavelengths BD equal to m plus 1 over 2 whole bracket lambda. Therefore, d sin theta equal to m plus 1 over 2 whole lambda. The first dark fringes in this case will obviously appear for the m equal to 0, second dark for m equal to 1. The interference patterns formed in the Young's experiments show the fig 19.3d. Equation 9.1 and equation 9.2 can be applied for determining the linear distance on the screen between adjacent to bright of the dark fringes. If the length of theta is small, then sin theta approximately tan theta. Now from fig 19.3, tan theta equal to y over lambda, where y is the distance of the point P from O. If a bright fringe is observed at the point P, then equation 9.1 y equal to m lambda L over D. If P is to the dark fringes, it is proved that Y equal to curly bracket M plus 1 over 2 curly bracket close lambda L over D. Therefore, delta Y equal to delta L over D. If the separation D between the two slits, the order of a bright of a dark fringe and fringe spacing delta Y are known, the wavelength lambda of the light is used. The interference effect can be determined by applying equation 19.5. For the mth bright fringes Ym equal to m delta L over D, and therefore for the m plus 1 the bright fringes Y into m plus 1 curly bracket m plus 1 lambda L over D. If the distance between the adjacent bright fringes is delta Y, then delta Y equal to m delta m plus 1 minus ym equal to m plus 1 curly bracket close delta L over D minus m into delta L over D. At least therefore the final result delta L over D equal to delta Y.